Uh, Good afternoon, everyone. I'm very happy to welcome our today's speaker, Professor Rajarama Bhat from ISI Bangalore. Before starting with the talk, I would like to request you all to keep your audio on mute. There will be a question answer session at the end. Nevertheless, if you want to ask any question in between, please do it over the chat box or use the raise hand feature and wait for a signal from Dr. Isan Patri before unmuting your audio. So let's start. Welcome, Professor Bhat, and please.
Thank you. So I'm very happy. So normally I would have gone to Delhi to give this talk, but now from Bangalore. So let me begin with some acknowledgements. So this is a joint work with the Tathagata Banerjee and Manish Kumar. Tathagata Banerjee is postdoc here and Manish Kumar is my PhD student. And I would like to thank the JC Bose Fellowship for research funding. And I would like to thank the organizers for the invitation, Tanvi and Isan. So, and this is a talk based on a preprint which is there in the archive. I'm just given you the link. Okay, so let me get into the talk. So we are studying C-star convexity of POVMs and UCP maps. So there are abbreviations here. So I have to tell you what are these POVMs or positive operator valued measures. I'll explain that first. So then I go to UCP maps, that is unital completely positive maps. Okay, so our goal was to study UCP maps actually for wanted to understand some extreme points of these CP maps, but we ended up that we have to study some POVMs to do that. So they are connected. So how are they related? So I will explain that. So first I will start with POVMs and then UCP maps and show how they are related. So then we come to C-star convexity and see, describe what are the results we have. And finally, one or two open problems. Okay, so this will be the scheme. So let me start with POVMs. Okay, so here is the basic definition. So you start with a measurable space. So that is X is a non-empty set and OX is just a sigma field over X. Okay, so that a measurable space and a Hilbert space H. Okay, so you have a measurable space and a Hilbert space. So then a POVM or positive operator valued measure on X. So with values in V of H is a map mu on the sigma field, okay, which satisfies the following properties. Okay, so mu of A should be positive in the sense of positive semi-definite sense. So it should be positive in V of H for all A measurable. Okay, in the second, you should have a measure, right? So this is measure in a very weak sense. So if you fix any two vectors H and K in H, mu HK is the inner product of the matrix entries of mu of A acting on K inner product with H. So this should be a regular, just a complex measure in the usual way. Okay, so it is a scalar valued measure. So for every vector H and K, it's a scalar measure. Okay, and mu of A is non-negative. That's all. Okay, so this way we are not really talking about measure as operators, but just in the weak sense. But that is good enough. Okay. Basic example, we have the spectral measures. If you have normal operator, then the spectral measures is a projection valued measure. So only difference here, instead of projection valued, we are taking positive operator valued measures. Okay. So here the spectral measure is supported on the spectrum of the operator. So like if you self adjoint, it will be on the real line. Like that you can have any measurable space X. Okay. So this is POVM and they are called generalized measurements in quantum theory. So the spectral measures, These usually called as the classical measurements, and sometimes they have to consider this kind of generalized measurements. So there is actually extensive literature on POVMs in physics. Okay, so some little bit of terminology. So you see this mu, the POVM mu is determined by mu hk, because if you have all the matrix entries, I know the operator, right? So it is mu is always determined by this. So I will always mu hk would denote these scalar measures. And mu is called normalized if mu of the whole space is identity. Okay, and it is projection valued measure, or PVM, if mu of A is a projection for each A. Okay, so all the values are projections. And then it is spectral measure if it is a PVM and is normalized. So it is projection valued and the mu of X is identity. So then it is spectral measure. Okay, and then sometimes we need to talk about the regular POVMs. So regular here in the measure theory sense, that is, so when you have X is a topological space, then I would take O of X as the Borel sigma field. And then these measures mu HH are all regular. Regular means mu of HH of any set you can approximate using compacts from below and from open sets from above. Okay, it's a technical condition, but it appears in Rees representation theorem, and so you need it sometimes. Okay, but you may ignore it for now. Okay, now you just remember that just mu HKs are regular, just measures. Okay, so then we come to UCP maps, or unital completely positive maps. I assume that most people here know it, so I'll just give the definition just for completeness, that's all. Okay, so A is a unital C-star algebra, and B of H, the algebra of bounded operators on a Hilbert space. Then a map phi from A to B of H, a linear map, we call it completely positive if phi on all matrices of Aij with entries from A, that should be non-negative whenever Aij is non-negative, and this should hold for every n, okay, all matrix sizes. So then you call it CP. So if an addition mu of the identity is identity, then it is unital completely positive map. Okay, so UCP map. So as I said, there is some correspondence, the relationship between the two. So let me explain that. So suppose X is a compact Hausdorff space and H is a Hilbert space. Then there is a nice correspondence between these regular POVMs and the CP maps. Okay. So given a POVM, okay, I can get a CP map. How do you do it? So suppose you have CP map on the space of continuous functions on X, right? X is a compact Hausdorff space, so continuous functions on X is a C-star algebra, unital C-star algebra. So we'll get a CP map on that. How? So given any function f, mu continuous function f here, I can integrate, right, with respect to the measure. So that will give you the matrix entries of phi mu acting on f. So it will give you an operator. You can estimate and you get a bounded operator. And whenever f is positive, it gives you a positive operator. So you get a positive linear map from Cx, the continuous functions on x, to B of h. And since this is a commutative C-star algebra, it is automatically completely positive. So given a POVM on the Borel sigma field, I get a CP map. Okay, and you can go the other way also. So given a CP map from C of X to B of H, then again you look at the matrix entries, you will get linear functionals, right? F goes to this phi of X acting on K inner product with H. So the matrix entries, that gives you linear functionals, and when you take H, K equal to H, it will be positive linear functional. So the Rees representation theory works. You can write it, you get a measure, and you can write it as an integral. So using these measures, then you get a POVM, positive operator valued measure. So this way, there is a one-to-one correspondence between CP maps on C of X and regular POVMs on the corresponding Borel-Sigma field. All both always taking values in the same B of H, right? There is a nice correspondence. So this is what we would exploit. Actually, this is a well-known thing. So you find it in book of Paulson, for instance. Okay, it's quite well known. Okay, so then we come to convexity and C star convexity. Okay, so here I will denote this PHX is the collection of all normalized POVMs on U of OX. Okay, so this corresponds to the UCP maps, the same kind of thing, but normalized positive operator valued measures. Okay, so clearly it is a convex set, right? If you have two measures, you can take their convex combinations, the positivity is retained, and you get another POVM. So it is a convex set, the collection of all normalized POVMs on OX. So what are its extreme points? Okay, it's a natural question as to what are the extreme points of normalized POVMs. So spectral measures are extreme actually. One can, in fact, we'll see that later. The spectral measures are extreme, but they are not all. Actually, there is no explicit description for all extreme points, even when X is finite set, just n points, I think more than 2 points. Then there is no full description. There is some abstract characterization, I'll come to that, but there is no nice description of as to what are all the extreme points, okay, of this normalized POVMs. But this is usual convexity. There is a notion of C star convexity. So what is C star convexity? Suppose I have n POVMs, mu1, mu2, mu_n, and n operators t1, t2, tn satisfying summation ti star ti equal to identity. Then you can look at mu acting on any point as summation ti star mu I and then ti. Okay, so it is like, looks very much like a CP map, but it is like a convex combination. If these ti's were scalars, it would be a convex combination because I have this condition summation ti star ti equal to identity. So ti's, instead of being operators, if they were scalars, I would get a usual convex combination, right? So these are called C star convex combinations. So the coefficients in the convexity, instead of being scalars, are now operators. If these operators are, we call them C star coefficients. If these operators are invertible, then the sum is called a proper C star convex combination. Okay, so it's called proper, this convex. Very often you need these TIs to be invertible. So then you call it a proper C star convex combination. Okay, so this notion of C star convexity has been around actually for a long time. Goebel and Paulson in 1981, that was the earliest we could see the reference. And in recent years, there is a lot of literature on C star convexity. But this C star convexity of Goebel and Paulson, etc., means they are studying just operators or elements of a C star algebra, C star convexity with respect to that. Whereas now we are talking about C star convexity of maps, okay, not the elements of C star algebra. So, and this P of X, it is a C star convex set in the sense it is closed under C star convex combinations. Okay, that's clear, right? See, if you take C star convex combination of POVM, you will get another POVM. And the condition summation ti star ti equal to identity says that if each of them are normalized, then the convex combination is also normalized. So what is the definition of extreme point here? It requires slight modification from the usual, and this is taken from this definition of Ferencz and Morens. They had defined it for UCP maps, but the same definition, essentially the same thing, works for POVMs. So this you have to pay attention to this because this is the main concept which we will be talking about throughout. So a normalized POVM mu is called a C star extreme point. So if you write it as a C star convex combination, summation ti star mu I ti. So if you write it as a C star convex combination, okay, of proper C-star convex combination. So the Ti should be invertible. So if you write it like this, then each mu I cannot say mu I should be equal to mu, but each mu I should be unitarily equivalent to mu. So that is, there are unitary operators ui such that each mu I is unitarily equivalent to mu. Okay. So like with the usual convex combination, when you have extreme point, you write it as a proper convex combination. Every term would be equal to the extreme point. Here I cannot have it to be equal to the extreme point because I can always change this by putting a unitary here, right? Because, so that is why this much freedom you have to give. Okay, so when we say C star extreme points, these coordinates, this individual terms mu I would be unitarily equivalent to mu. Okay, so this is the definition. I'll just give you 2 minutes to have first look at this, because this is the most crucial thing, because throughout we will be studying C star extreme points of POVMs. Okay, so this is a definition. So if mu equal to this summation Ti star mu I Ti, where each Ti's are invertible and summation Ti star Ti equal to identity, it should mean that each of the mu I is unitarily equivalent to mu. Okay. So we will see that the spectral measures are C star extreme. And are they all? Okay. That is a natural question, because we saw that with respect to usual extreme points, or we call sometimes as the classical extreme points or the usual extreme points, spectral measures are not the only extreme points. There are other extreme points. But what about now? So we have given more freedom in taking scalars here, right? Instead of scalars, we have operators. So what can we say now? We know that spectral measures are C star extreme, but is it everything? So the main theorem which I want to present is that under good situations, C star extreme POMs are spectral. Okay, so the spectral measures are the extreme points, the C star extreme points. Okay, but of course, this theorem has no meaning unless I tell you what this under good situations means. So like good situation 1 is that for arbitrary x, when h is finite, okay, as long as the Hilbert space is finite, whatever the x, the C star extreme POVMs are spectral measures, the projection valued measure. Okay, so this was known when x is compact and Hausdorff through the theory of CP maps by Teranic and Morens. So when x is compact and Hausdorff, so now we have extended it for general x. Another good situation is x is countable set, but h is infinite dimensional. Okay, so this was not known even for finite sets. So even just for 2-point sets it was known. For 2-point sets is easy because you have get some commutativity automatically. But more than 2-point set it was not known when h is infinite dimensional. Of course, h finite dimensional, this would give you the result. But h infinite dimensional, it was not known even for finite sets, that is about CP maps on Cn. It was not known. So now we are able to do it for arbitrary countable set. You would think then, okay, maybe this is true all the time, right? And that is not true. There are non-spectral C star extreme points. When you take the space as, say, the interval 0 to 1 or the circle, okay, with h infinite dimensional. Of course, with h finite dimensional, it's not possible. But with h infinite dimensional, even with simple spaces like an interval or a circle, there are C star extreme points which are non-spectral. We still don't know how to describe those non-spectral C star extreme points. But what we would look at now is basically these situations. Okay, these two, good situation 1 and good situation 2, how to tackle them. Okay, so I have to cover some basic theorems on POVMs. First one is the Naimark's dilation theorem. So you start with the POVM. So then there exists a triple pi, v, and h pi, where h is a Hilbert space, pi is a spectral measure, and v is a map, bounded linear map from H to H pi. And mu of A is V star pi A V. Okay. So what this is saying is that all POVMs essentially come from spectral measures to restrictions, to compressions, right? So all POVMs, like you take an arbitrary POVM, there is a spectral measure in a bigger space, and mu of A can be recovered from a spectral measure. And there is a minimality condition, that is, if you apply pi OX on V of H, the span closure, that should be whole of H. And such a dilation is unique up to unitary equivalence. So the triple is called the Naimark dilation triple for mu, because it's unique up to unitary equivalence under this. And pi is spectral, so V is an isometry. This is, if you put A equal to X here, then this is identity. So V star V is mu of X. So if mu is normalized, then V is an isometry. So this theorem, if you have studied CP maps, immediately you will be reminded of Stein-Spring dilation theorem. So this is a POVM analog of Stein-Spring's representation theorem for CP maps. Okay. So in Stein-Spring representation says that CP maps come from star homomorphisms. So here we are saying POVMs come from spectral measures. Okay. And if you see Paulson's book, he derives this theorem, Naimark's dilation theorem, using Stein-Spring's representation theorem. So that is possible. Only issue is that when you do it that way, you get only regular POVMs. The measures are going to be regular. The general one you don't get, but because when you go from CP maps to this, that is what happens. You get only the regular one. So, but general thing, the proof is not difficult. The same kind of proof can be given. Then another theorem, like for measures, you have Radon-Nikodym theorem. There is a similar theorem here, Radon-Nikodym type theorem, I'm saying it. So mu is a POVM, okay. So with say minimal Naimark dilation, pi V H pi. Then you take another POVM, say nu, which is dominated by mu. Okay, so that means nu is a POVM. Also, nu is less than or equal to mu. That is mu minus nu. That is also a POVM. Okay, so you assume that. So that that happens if and only if there is a positive contraction D, which commutes with the range of pi. So this is the commutant. Positive contraction D, which commutes with the range of pi, and nu of A is given by V star D pi A V. So this D you can write either here or here, because D commutes with pi of A. So nu of A is given by this. In other words, all POVMs which are dominated by mu are given by contractions in the commutant of the range of pi. Okay, you take pi of A, the all correction. In the commutant, you take a positive contraction. You can multiply by that and compress, then you get mu. So all the, it is not exactly Radon-Nikodym theorem, because in Radon-Nikodym theorem, you don't compare the values of nu and mu. Just say that mu of something is 0, then mu of the same set is 0. That is what is said in the Radon-Nikodym theorem. But here we are saying mu is less than or equal to mu, so the difference has to be positive. Okay. Now, a similar theorem for CP maps was proved by Arvesen in his famous paper, that subalgebras, star algebras. Same kind of result. Okay. Instead of mu nu, here you have CP maps and Stein-Spring representation. Okay. And I'm saying this theorem is really folklore in the literature for POVM. All that means is that you can find it in many places, and we haven't taken the trouble to find out who exactly proved it first. So I don't know. Okay, but the proof is similar, like the Arvesen's theorem for CP maps, similar theorem. Okay, so this gives us the extreme point criteria. So this I am talking about now, the usual extreme point, not C star extreme point. So you take any mu, take the minimal Naimark dilation, then a necessary and sufficient criterion for mu to be extreme is that this map from the commutant, okay, d goes to v star dv from the commutant of range of pi to b of h, that should be injective. Okay, v star dv equal to 0 implies d equal to 0. Okay, so that is a, so if that happens, then this mu is extreme and vice versa. Okay, so this kind of abstract criteria is there, but it doesn't tell you exactly when mu is extreme. It's difficult to see. Again, this is also well known, and a similar theorem for CP maps was proved by Arvesen, okay, for the extreme points of Arvesen. And in fact, you can also see some work of Kyapatsarathi and others, where they are used, they have similar kind of theorem to characterizing extreme points of CP maps using Krauss representation. Okay, all means this is a general one for general CP maps and general C-star algebras or POVMs. Okay, so an immediate corollary of this is that every spectral measure is extreme, because if you take spectral measure, if you start with the spectral measure, then the dilation is itself. Okay, so pi becomes just the identity map. So this is automatic. This map is the identity map. D goes to D, so that is injective. So every spectral measure is extreme. Okay, so because the dilation is itself. Okay, that comes out easily. So now need C-star extreme point criteria. Similar thing for C-star extreme points. So this was proved by Ferencz and Zhu. Again, they did it for CP maps. I have presented it here for POVMs. Okay, so you take a normalized POVM mu. So that is a C-star extreme point if and only if something happens. Okay, again, something about D in the commutant. So any D in the commutant such that V star dV is invertible, D has a special form. Okay, I'm not talking about injectivity. D has a special form. Okay, so there is some co-isometry used. Actually, you may ignore this. Okay, this condition looks complicated. You may ignore it. And I also give you a warning, like in paper of Ferencz and Zhu, they don't say this U is co-isometry. They take it to be a unitary. We couldn't figure out how to get unitary there. You get only co-isometry. And this also immediately tells you that every spectral measure is a C-star extreme point. So why am I saying that you may more or less forget this? Because I will not be using this. I will be using the next one. It's a corollary to this, and it comes from this and by Zhu, which is you can understand better. Okay, so here it is. So if you take a POVM mu, it is C-star extreme if and only if any nu dominated by mu has a form like this. Nu of A is T star mu A T for all A. So anything dominated and nu of X invertible. Okay. Under these two conditions, any POVM dominated by mu such that nu X is invertible, nu should have a form like this. Nu of A equal to T star mu A T. Okay. For some invertible operator T. Okay. So this is the criteria. Okay. This follows from here. And again, in Zhu's paper, it was not clear exactly whether you need this invertibility or not. He seemed to say that this kind of decomposition works for always, whenever nu is dominated by mu. But that by mu and nu x invertible, nu has a form like this. Nu of A equal to T star mu A T. Okay. So this will be the criteria. Okay, we will use this criteria to identify C-star extreme points. Okay. So using this criteria also, you can see that spectral measure are C-star extreme points, because then the dilation here is well. Let me not go into that. Let me go to the next thing. This is what called the crucial step, the main theorem, okay, or the main step which gives you all the other theorem, most of the theorems we have follow from this theorem. So what does it say? So let mu be a C star extreme. It's a characterization of C star, the value of mu at some points. So let mu be a C star extreme point. Okay. If a set E is such that mu of E commutes with all mu of A, where A is contained in E. Okay. So I need to look at only those sets A which are contained in E. So mu of E should commute with all mu of A, then mu of E is a projection. Okay. So that is the statement. If you have a C star extreme point, look at mu of E. If it commutes with all the mu A's where A is contained in E, then mu of E must be a projection. For instance, when you take E to be a singleton, okay, if this E is a singleton, then you know that mu of empty set anyway has to be 0. So this commutativity is automatic. So this theorem immediately tells you that mu of singletons for C star extreme points, mu of singletons are always projections. So that's why immediately you get results for countable sets, okay, the finite sets and countable sets, etc. Mu of singletons you will get as a projection here. Okay. So here is I give you some idea of the proof, how we see that this is a projection. So that is using functional calculus. So what we will show is that to fix any R and S between 0 and 1, we will show that the spectrum of mu of E intersected with this interval R to S is empty. Okay, and this is true for any R and S, okay, between 0 and 1. So that will show that mu of E does not intersect with any point in between 0 and 1. So in other words, let me go up. So in other words, mu of E can, it's anyway, it's a positive contraction. So only things in the spectrum of mu of E is the 0 and 1. So it is a projection. Okay. So how do we show that this holds? So we choose a function f in the interval 0 to 1. Okay, you define this function. Now this is a very carefully chosen function so that something happens later, which you'll see. So, so what sort of function is this? So given this R and S, so the whole proof is this fix this R and S. So the ft is just the constant one outside the interval R to S. Within the interval R to S, at t equal to R, if you put t equal to R, you see that you get 1 itself. So it's the constant function 1 up to R, then it just goes down. The function goes down to some value, okay? And then at S, it's again 1. So the f is continuous except one point, namely S, okay, at this endpoint. So it is 1, just the constant 1 up to R, then goes down, okay, continuously to some value which is called as alpha at S, then again jumps back to 1, okay, after S it is 1. So it is continuous except one point, namely S, and hence Borel measurable. See, we had to do this, and for this reason, the construction will not work when you talk with C star setup. We need to take measurable setup. You can't do this with continuous functions. Okay. So anyway, so this function f, what we have defined, what you need to remember is that it is measurable and it is strictly positive. The minimum value is this value attained at S. It is strictly positive and less than or equal to 1. Okay. So for any positive contraction t, I can define f of t, and that is greater than or equal to alpha times identity and less than identity. Okay. It is invertible. For any positive t, f of t is invertible. Okay. So now we define a map nu like this. So nu of any set B is mu B intersected with E. I apply the F on mu of E, and I don't change the mu outside of B. Okay. So in other words, I am changing the measure inside E. And when I change inside E, see, mu of B intersected E, it commutes with mu of E. That was the assumption. Okay. And this is function of mu of E. So I can take this whichever way I want, I can bring it this side. So this remains positive because f of something positive is positive, this is positive, and they commute. Okay, so this is where we crucially use the commutativity. So, and we need the commutativity only for subsets of E. And we show that this nu defined this way is a POVM, and nu x, if you put x here, it is invertible, and nu is less than or equal to mu. So Zhu's criteria is applicable. You have chosen the function f such that it is a POVM and mu x is invertible and mu is less than or equal to mu. So by Zhu's criteria of C star extreme points, there is some t such that nu of b is t star mu b t for every b. Okay, so the dominated measure is given by conjugation by some t. So we look at the polar decomposition of t. So write t as u times mod t. Now remember, Zhu's criteria tells that you can get an invertible t. So this u is a not just a partial isometry, it is a unitary. And you know what t is because you know what mod t is. You see, because here if I this is given for every b. So if I take b equal to x, okay, nu of x, that will give you t star t, right? And nu of x, you put the x here, then what you get is this mu of e plus f of mu of e plus mu of the complement is 1 minus mu of e, because mu of the whole space is 1 identity. So I know what mod t is. Okay, so I know what mod t is. It is a function of mu of e, and the other part is a unitary. So you put them together. So we have then t star mu e t. Okay. So I have evaluated this nu at x, b equal to x, and you also evaluate at e. Okay. So if you evaluate at t, at e, I get this t star mu e t. So of course you have the polar decomposition t equal to u mod t. You put it, and then you get the other end. If I put b equal to e here, this part is 0. I get mu of e, f of mu of e. So everywhere I'm getting mu of e. You just give a name to that. So it's some positive operator s. Okay. So and I want to know about its spectrum. So what we have, you just take this mod t is a function of s, right? Is this function of s. So I can take it to the other side because it's invertible. So this side you just have then u star su, and the other side you have some function of mu of e, another some function of s. So you compute that function g. So that function is explicitly it's given here. So you get u star su equal to g of s, where g is this function. So look at the function. So it is the function is t outside the interval r to s, and it's r when it is inside the interval r to s. Okay. So outside is just the identity function t, and inside it is r. So it is just the t all the way up to r, then constant r, then again jumps to s. So whatever it is, it's a function which does not take any value within the interval, within the open interval r to s. All its values are outside the open interval r to s. Okay, and what we have here is that g of s is unitarily equivalent to s. Okay, I don't care what unitary is, but g of s is unitarily equivalent to s, and g of t does not take any value within the interval r to s. So by spectral mapping theorem, spectrum of s is same as spectrum of u star su, u being a unitary, and that is spectrum of g of s, because g of s unitarily equivalent to u star su, and the range of g is contained here, 0 to r and s to 1. It has no point within the interval s, r to s. So this f was chosen initially. I said we carefully choose f so that this happens when you come to g. Okay, so after, it's back calculation. When you finally compute g, I don't want any value within the interval r to s. Okay, so this means the spectrum of s, since it is same as spectrum of g of s, and g doesn't take any value within this. So by functional calculus, spectral mapping theorem. Spectrum of S is contained in here. So in other words, spectrum of S intersected with R2S is empty for all R and S. Since this is true for all R and S, the spectrum of S consists of only 0 and 1. So it is a projection. So that is what, okay. So that was the main theorem. So I wanted to spend some time on that just to explain the proof. So now we see the consequences. One is that we have the we want to have the situation where mu of E commutes with things inside. So one such situation is the atomic ones. Okay, a subset A is called an atom for mu if mu of A is not 0, and whenever B is contained in A, mu of B is either 0 or mu of B is same as mu of A. Then you call A as an atom. And you can see that as soon as A is an atom, you can apply the previous theorem. So it is applicable because anything contained in A, mu of B is either 0 or mu of A. So in particular, it commutes with mu of A. So if you have a C star extreme mu, then mu at any atom has to be a projection. So you call the whole POVM mu as atomic if for every A with mu of A not 0, it contains an atom. Then you call it atomic, and it's called non-atomic if it has no atom. Okay, and every POVM decomposes uniquely as a sum of an atomic POVM and a non-atomic POVM. Such theorems are there for in measure theory, usual measure theory, and they have been extended to this. This is not ours; it is known theorem. So now, applying the previous theorem, we get this: an atomic normalized POVM mu on a measurable space X is a C star extreme point if and only if mu is spectral. So in the atomic case, the extreme points have to be spectral. You have to have projections. In particular, if X is a countable measurable space, then any C star extreme point is spectral. Okay. So these are the theorems which I claimed before. They all follow from the previous theorem. And here is something extra. Or something additional. If mu is such that the range of mu is commutative, then again that theorem, previous theorem is applicable, and you see that if mu is C star extreme and mu of every set is means they are from a commutative family, then it is a spectral measure. Such theorems have been proved for CP maps. So we have a similar theorem. If you know that it is C star extreme and the range is commutative, then it is a spectral measure. So now we come back to CP maps, okay, because that is what we wanted to study. So C star convexity of CP maps. So now the setting, you don't take a general set X, but a compact Hausdorff space, and you look at UCP maps on that, unital completely positive maps, taking values in V of H on Cx, on the space of continuous functions on X. Okay. So again, that's a convex set. In fact, that is a C star convex set. If you have phi's are all UCP maps and some ti's are there, some bounded operators. So there's summation ti star ti equal to 1. Okay, summation ti star. Then this is a C star convex combination of UCP maps phi's, which is again UCP. So here is the original definition of Ferencz and Moritz, which defines C star extreme points of UCP maps. So a map phi is C star extreme if whenever you write it as a C star convex combination where ti's are invertible, so proper convex combination with summation ti star ti equal to identity, then each phi is unitarily equivalent to phi. Okay, there exists unitaries. This is just analogous to what we had done for measures, right? So same definition. So this is what they were studying, and what we wanted to study also. So, and we have the correspondence between the UCP maps and the POVMs. So if you can see that correspondence retains these extreme points and C star extreme points. So a normalized regular POVM is C star extreme if and only if the corresponding map is corresponding UCP map is C star extreme. So you can go back and forth. Okay, so you can deduce theorems for UCP maps by studying POVMs and vice versa. So, so what results we have for UCP maps? So every unital star homomorphism is a C star extreme point. This was proved by Ferencz and Morens, and that is analogous to saying that the spectral measures are C star extreme. Okay. So then, if you have a commutative unital C star algebra with countable spectrum, okay, and phi is UCP, then phi is C star extreme if and only if phi is a star homomorphism. So this is we could prove because here we have assumed countable spectrum. So if you go to the corresponding POVMs, you will get to the countable X. Okay, A would be, this is a commutative unital C star algebra with spectrum, countable spectrum. You call it X. So A is isomorphic to continuous functions on X, and we are considering POVMs on X, and X is countable. So there you get spectral measures. So by the correspondence, you get star homomorphisms. As I said, this was not known even for finite Cn, the algebra Cn. Okay. So we apply this to a special case. We apply this to the C star algebra generated by a single normal operator n. Okay. So let n be a normal operator on a hyperspace K with countable spectrum. Okay. So this is a Cauchy condition, countable spectrum. And you look at the C star algebra generated by n, the unital C star algebra generated by n, and we look at a specific CP map. Okay. So take a closed subspace H of K. So we look at the CP maps to B of H. Okay, here is the CP map. It is just compression. Phi from C star n to B of H. Apply T on H and compress it back to H. So it's a compression of T. So which is clearly a unital CP map. Okay, and we have this. The following are equivalent. Phi is a C star extreme point. If and only if phi is a star homomorphism, and that happens if and only if H is invariant subspace for n, and that happens if H is co-invariant, and that is H is reducing. So all these are possible because we assume that n has countable spectrum. So with that, this invariant subspace would also be a reducing subspace. Okay, and you get star homomorphism. So all these things become equivalent. So you would ask, what if I don't have countable spectrum? Okay. Right, that's a natural thing to ask, and here is the Hardy space example. Consider the Hardy space H2 on the unit disk, considered as a subspace of L2 of T. The usual way, the Hardy space H2 consists of analytic functions with only the non-negative, this Fourier coefficients. The negative ones are not there, and L2T has everything, so it has the subspace of this. And you look at the compression map, continuous functions on the circle. So you have the corresponding multiplication operator, and then compressed it, multiplication operator on the L2, compressed it back to H2. Okay, so it is exactly like the previous example for the normal thing. Only thing is that now the spectrum is the circle. So okay, which is not countable. So it is known that this phi is a C star extreme. So it's a very standard example. So when I said that there are C star extreme points which are not homomorphisms, you would think which are not, say in the case of POVMs, not spectral. You would say the examples might be very complicated or exotic. No, that is not the case. Very natural examples are there where the extreme points are not spectral for POVMs and not star homomorphisms in the case of C star algebras or for UCP maps. So this example was shown to be an extreme point by Arvesen. Okay, in the same paper, I think he used this example, and Ferencz and Morens show that this is a C star extreme point too. Okay, so this does not come under our study because the spectrum is not countable. Okay, so and what we can do with this is that, see, we have been doing measure theory. So in measure theory, like the interval T is, or the circle, unit circle T is isomorphic to the interval 0 to 1. So, and you can go to any other space which is measure theoretically isomorphic. You don't need isomorphism up to topology, but just measure theoretic isomorphism is enough. So using that, we can show now that you take any separable commutative unital C-star algebra with uncountable spectrum. So instead of countable, you have uncountable spectrum. Okay. Then with H infinite dimensional, there is a C-star extreme point which is not a star homomorphism. So once you have this example, one example, you can move to any other uncountable spectrum space. But there are some conditions here. It is separable. And, the H should be infinite dimensional, of course. If it is finite dimensional, it would always be star homomorphism. Okay. So, and this is still a mystery for us, this example of Hardy space, because we would like to understand as to what are all the C-star extreme points, say in this case. So we don't know. We know that we have some examples of C-star extreme points which are not star homomorphisms, but how does generally it look like, even for the case like this, continuous functions on the circle, we don't know. How exactly all the C-star extreme points look like, we don't know. Okay. So here I come to an open problem. So are C-star extreme unital completely positive on the C-star algebra L infinity, always a star homomorphism. Okay. So the C-star algebra is L infinity, and it looks countable, but if you see the spectrum is the Stonzek compactification, which is not even metrizable. So, and we don't know how to handle it. So this is a basic question. You look at UCP maps on L infinity. Okay. So taking values in V of H, where H is infinite dimensional, can we say that the C-star extreme points are always star homomorphisms? So we don't know. We have to really understand this Stonzek compactification better to do that. So we don't know how to do that. Okay. I also would like to say the paper has several other results which I didn't talk about, there is the results about things like measure isomorphism, which I didn't speak much, and then there are results about Crane-Millman type theorem. You want to approximate every POVM through the extreme points or C-star extreme points, or same way you want to approximate every UCP map using the C-star extreme UCP maps, okay, in suitable topology, and that can be done. So Crane-Millman type theorem, so that is also there in paper. There are several other sections, but I thought it's better to concentrate on the main things. And actually I'm more or less completing before time, almost 5 minutes before time. Maybe it's good. Like if you have questions, I get done. Yeah.
Thank you, Rajita.
Yeah.
I think Professor Singh has some questions. I could see in the chat box. So
let me see.
Professor Ajit ma'am, or she could, ma'am, you can just unmute your audio here.
Oh, yes, I have unmuted now.
Yeah, thank you.
Yeah. No, the very wonderful talk. I enjoyed it very much. It's a wonderful talk. Now, for atomic and non-atomic measures, I have this remark that for a countable space like natural numbers, you can have atomic measures whose range is convex. Like you send a singleton n to 1/2 raised to n.
Okay.
Then the range of this measure is convex and it is atomic measure. Now the sequence 1/2 raised to n can be replaced by many other sequences, like 1/q raised to n, where q lies between 1 and 2.
Okay.
But if you go to q bigger than 2, then the range stops becoming convex. We know for Cantor set, if you assign 1/3 raised to n, then the range is Cantor set, which is not convex. So there is a lot of literature on interval filling sequences. It was started by Kakeya a long time ago, more than 100 years, a long time ago. And then, continued by Katok and other people. Now my student Laltan Puya and myself took up the study of Lyapunov convexity theorems. When is the range of a vector measure convex? That is famous Lyapunov convexity theorem. So we have 2 papers, and I can send you people the papers. And in the second paper, which is in journal Convex Analysis, we consider these interval filling sequences. And in the first paper, we consider vector measures coming geometry of the vector measures, and there is a lot of literature on matrix valued vector measures and also operator valued vector measures. And as I wrote in the chat, there is Lyapunov convexity theorems by Ekman and Anderson. It is Memoir AMS number 498, and they use completely, you know that, okay.
I'll have a look. I don't know really. I know that there are theorems about this convexity of the range. But,
yes, good. Then you know.
But I don't know what it means for positive operator valued measures. You have to see that.
Yeah, you see what it is that for atomic, they will take atomic Feynman algebras, you know, commutative, and then they will take completely positive maps from one operator algebra to another, and the range is usually not convex, okay, even for 2 cross 2, you know, the trouble starts, and examples are given there. And what Laltan, Puya and I did, you know, you forget about non-atomicity, atomicity or non-atomicity, because atomic measures can also have convex range, because these people were measuring the non-convexity, you know, radius of non-convexity for atomic measures, whereas we took atomic measures coming from interval filling sequences also. And there is a lot of work by Hill, and he visited here. And I mean, there is enough material that I know from old days. After 2008, I haven't worked in this area. Up to 2008, I have information.
Yeah.
And is that helpful?
Yeah, definitely. We would look it up. We have just studied it recently only.
Okay. Thank you.
Any other questions? Yes.
Yes, I mean, Sophie here.
Hello, how are you?
Good, Rajaram. Nice talk. I mean, just continuing from where Professor Singh left it, there are situations where certain operator valued measures do have convex ranges. I mean, like the vector measures, the spectral measures, which arise from the so-called continuous streams. And but then we don't have a complete description of those non-atomic POVMs where it happens. But then there are isolated situations where Lyapunov does hold. I mean, especially in case of POVMs, which arise from you know, these continuous frames.
Okay.
Any other question?
I have one question.
Yeah.
So the initial few slides, I'm sorry, because the people were coming and I was doing this, so I might have missed some point. But it looks to me that the way you defined it, POVM should be analogous to a normal UCP map on L infinity when you take the L infinity with respect to the measure space, right?
I'll go back to the definition. So this is the definition.
Yeah. Okay. So basically, each so projection in the L infinity, I mean, because so the sets correspond to projections, you're sending to positive. So essentially, because these projections will span the L infinity, so you will end up getting a positive map on L infinity, which will become completely positive. And the measure part, I'm guessing, will give the normality of that.
Yes.
So then, if it is corresponding directly to normal UCP maps with on this, so then from the UCP results, you will end up getting many of the results directly for POVMs. No, like for example, the Radon-Nikodym, because that looks exactly like what we have for one-Neumann algebras.
Yeah. It is true. Means there is a very strong correlation between the two. Okay. But I think some things will not work. That is, when you go to there, I think you might need the regularity of the measure, right? You might need the regularity of the measure.
Yeah, it's quite. Yeah. I think so. Yeah. Probably.
If it's not regular, then you may not.
Yeah. I think that is probably a point. Yeah.
I want to say something more too.
Yeah, sure.
You see, there is important notion of symmetric, informationally complete, positive operator valued measures, SIC POVM as they are called, for finite dimensional setup, and extensive literature and a lot of literature by Grassel and Scott. And I'm glad to report that, you know, we have a long paper on archive now, 1411.0152. Chaturvedi Ghosh, Professor Pathasarthi and myself, where we consider, you know, projection of rank 1 valued basis derived from unitary basis. How to derive rank 1 projection basis from unitary basis in a concrete manner. We are not able to get SIC POVM, but we are able to get these bases with few angles. Symmetric informationally complete means all the angles, all the inner products are same. But we have restricted number of inner products. So if people like, they can look at this paper 1411.0152 version 3. And a lot of literature on SIC POVM. And for SIC POVM, if you want to start with the easiest possible introduction, I have a joint paper with Shiva Kumar and Manami Chatterjee, 1804.08100. It is a Fibonacci fervor in linear algebra and quantum information theory, which gives introduction to SIC POVM.
Good. Yes.
All right.
So, any other person? Any comment? Any questions? So if we have no more, let's unmute our audio and thank Rajada for a wonderful talk.
Thank you.
Thank you.